So, yesterday talked about work. Today, we're going to incorporate energy. Okay? So, by the end of this lesson, you'll be able to describe and calculate when something has kinetic energy, understand the relationship between network and the change in kinetic energy, and understand the relationship between speed and stopping distance. All right, so kinetic energy. This is the energy of motion. Energy of motion. The energy something has when it is moving. The energy something has when it is moving. Okay. The equation for kinetic energy Ooh, a little squeaker there, is 1/2 mass times speed squared. 1/2 mass times speed squared. All right. So, based upon that equation, does kinetic energy have direction? Sorry. This is an important detail. So that cursive V, this is speed. That script V is speed. So based upon that equation, does kinetic energy have direction? Does mass have direction? Does speed have direction? So kinetic energy does not have direction, therefore it is a scalar. Okay. This is actually a pretty user-friendly equation. So let's pretend you forgot that this meant speed and you just thought it meant velocity. And you had, like in the story problem, you had a dog is riding with a velocity of -3 meters a second. And you plug -3 in for the speed. But then you go to do the math. What happens to that negative sign? Becomes positive. So user-friendly equation, got your back, even when you don't. Okay, do that. So the units for kinetic energy, joule. Where do we see that before? Work. Wonder if there's a connection between work and energy. Probably. All right. So this is the work energy theorem. And this says the net work is equal to the change in kinetic energy. The net work is equal to the change in kinetic energy. Okay. So when we find the change in anything, what is that equal to? Like, how do you find the change? Final minus initial. So final kinetic energy minus initial kinetic energy. Okay. So if we were to unpack that, like full on, just like blah, put it all out there. Yesterday, we talked about how the net force it's parallel to the direction of motion times distance. That's equal to the net work, which is equal to the change in kinetic energy, which is equal to 1/2 mass times speed squared final minus 1/2 mass times speed squared initial. Woo! In textbooks, you'll see work energy theorem is just written like this, but like this incorporates fuller picture. Okay. So before we get overwhelmed with the huge long train of equations here, let's look at this conceptually. Okay. If an unbalanced force, a net force, acts on an object, what will happen to that object's motion? What will happen if there's an unbalanced force or net force that's not equal to 0 acts on an object? Tell your neighbor. Okay, I heard rumblings, which is good. It'll experience acceleration. It'll speed up, slow down. Yes. Okay. So its speed will change. Correct? Okay. So what will happen to the object's kinetic energy if that's the case? Will it stay constant or will it change? It'll change. Does that make sense? Because the speed is changing. Okay. So energy is a really big concept in science. And we've just kind of unpacked this idea that, hey, if a force acts on an object, it's going to cause the kinetic energy to change. And we're good with that, right? But then the follow-up question to that is like, well, by how much does it change? Like, do we know how much it changes by? Like, what's the quantity? Like, man, that would be really helpful considering we're trying to figure stuff out. Like, I know it's going to change, but by how much? And that is why we baked up this whole idea of work. Like, what is work? Well, it's just the quantity of force times distance. But when you take that force and you multiply it by the distance at which the force acts on it, that actually equals how much energy is changed by, which that's pretty powerful. Like, we know it's going to change, but we actually can now calculate how much it changes by. You with that? So that's big picture. Okay. So we're going to learn how to employ that. Okay. So what would make, just looking at this top line here, what would make the network positive? What would have to happen to the kinetic energy for the network to be positive? Tell your neighbor. Okay, correct answer is which is going to be more? To make it positive, your final is going to be greater. And to make it negative, initial is going to be more. Good with that? Okay. So we're back to dragging our box across the ground here. Same example as yesterday. This time, though, I'm going to be asking for how fast the box is going at 20 meters. Okay. Now, before we dive into this, I do want to address this. If you're reading this, you might be thinking to yourself, I'm pretty sure I could solve that with what I learned last chapter, drawing a free body diagram and like going through the 5 steps, solving for acceleration, and then taking that acceleration and sticking it into a kinematic equation. And I say to you, yes, you're absolutely correct. You could totally solve for that. Okay. Work and energy is a secondary approach, is an alternative way to solve this problem. Okay. For this chapter, I want you to do work and energy approach. Okay. When it comes time for the final, I don't care. You can pick either way. Okay. However, there are times, there's circumstances where last chapter stuff, free body diagram, acceleration, falls apart. And in order to actually evaluate it, you need to do calculus. Work and energy steps forth like, dun, dun, dun. You don't need calculus when you do my approach. And so it is a helpful, it's not redundant. It actually provides purpose or has purpose. Okay. So how fast will this be going? This box be going? So we know, so we have the net force times distance equals the net work equals change in kinetic energy equals 1/2 mass times speed squared final, or 1/2 mass times speed squared initial. Okay. Now, yesterday we already figured out that we came up with a value of this already. Positive 2,000 joules for the net work. We already did all that. Those calculations. Good with that? So if you were to start this from scratch, you'd have to figure that out. Okay. And that's going to be equal to, actually, before we start plugging in numbers, how would I go about incorporating started from rest? How would that manifest itself as we start to plug in numbers? Tell your neighbor. Okay. Heard a lot of it. That's good. Initial speed is 0. So if I plug in 0 here, what does that do to that whole expression? This all goes to 0. So it initially doesn't have kinetic energy. So you have 1/2 100 kilograms times speed squared. That's 50. So 50 divided by 2,000 is 80. Square root that. That's 8.94 meters per second. At least it was past 2 hours. I'm assuming that hasn't changed. Spring. Oh. The next problem. Good call. Thank you much. Okay, with that, 8.94 meters per second. Sorry, getting a little sloppy when I write down below. Good there? Questions, points of confusion. Okay, still dragging a box, but I'm changing it up a little bit. Notice I'm putting this equation up top here. Tell your neighbor. Okay, so you have 1/2 times 100 kilograms times 3 meters per second squared minus 1/2 100 kilograms times 1 meter per second squared. So you get 9 times 100 divided by 2, so 450 minus 1 times 100 divided by 2, 50. 400. With that, okay. Popular error is to disobey the orders of operation, subtracting and then squaring. Popular wrong answer is 200. Make sure you square before you subtract. Good. Okay. All right, so still dragging a box, but changing it up a little bit. Talk to your neighbor.
What you can do is accept the equations so you have the final equation that equal to sum of I'm trying to think of oh wait, yeah. Action and then like show how much friction. Yeah, that's fine. Yeah. That's the one.
Correct answer is? Correct answer is no. Okay. Here's why. That's going to give you your net force, your total force that's parallel to the direction of motion. If tension was the only thing acting on it, if tension was the only thing doing work, then yes, you could. But it isn't. Okay, there's other forces going on. Does that make sense? Now, if you were given friction, if you're given the value of friction, then you could find tension. But with what you're given, all you've got is the net force. Okay, good with that? Okay, give that one a shot. You want to do extended time or want the whole thing right now? Okay, go ahead and just put your bag and stuff over there. Go ahead and have a conversation. It's the same thing.
When I guess. So obviously we create you get because you're remember how that works. Well, I don't know. Okay, well if you reverse the charges. And then I guess also it would work because so right? It's a free spirit. And then the tether force also creates friction.
Okay. See, these are the questions that I always like say yes.
Me too. I'm gonna write this down.
This one Right now, I feel probably
If that was in like there.
Have you
What do you say?
Do you ever get
Not really, because I've seen it in my
Correct answer is C. Good job. So the net force, to find that, you're going to have force of tension in the x direction minus kinetic friction. In order to make this quantity negative, friction would have to be bigger. And over here, in order to make this quantity negative, you'd have to have more kinetic energy initially than when you started. So you'll be moving faster. Then in the end, so you're going to slow down. Good with that? So you got two different perspectives to look at network. You can look at the force distance side, or you can look at the motion side. Okay. Last question. We're going to have some extra time. How many people would like me to print out a worksheet for you? Okay. Have a conversation.
down the road, and then it takes a turn when you turn at the same speed. There's no change to force. Yeah, so it's no. Yeah, right. So that's fine. Yeah. So can't do zero. So yeah, that's no. And if it's like moving at the same speed that balance the entire time, or you could just like lift it on a street, like just like put it in reverse to go 60 miles. Right. So like where's the distance right now? No. And force nothing to do with direction. So it doesn't matter. But I'm thinking about the first one is no. The second one because the artwork is spinal bias.
so mass speed hasn't changed? So it's just I did not just
So both of them know.
no.
The second one also. You guys are direct. Same mouse and same speed, and all probably the same mouse. So That's why I teach you so well. Yeah. It's okay. Also, I see spirit university. On the mic. On the mic. It's really chill. Yes. It's like honestly murder. Does it start with an E? It's via hard something. Via something. It has travel. Oh wait, house. That's nice. Through the same through the same two V's. Through the same two V's. Through the same two V's. Like stole. My house got stolen. Yeah, it's like. What do you say? It was easy that was hard. Yeah, but it was like one the first one.
Here to C. What do we think? Here D. B and E. All right. So here is how this works. So let's just take it the sum of the forces. Did the direction of velocity change? Yes. Therefore, was there a change in velocity? Yes. It's a vector, incorporates speed and direction. If you change either one of those, that's acceleration. Okay, so you have a change in velocity, you have acceleration. The net force cannot be equal to 0. Okay, there is an unbalanced force, so yes, for the net force is equal to 0. Okay. Now, with work, does work have direction? Does kinetic energy have direction? No. Okay. So the correct answer is no. The network was equal to 0. Let me explain how that works. So you're driving along, going northward, and then you're like, oh, shoot, I need to go the other way. And so you're hitting the brakes, you're applying the brakes, like, are the brakes doing positive or negative work? Negative work. Okay. You stop, turn around, and then you speed back up. While you're speeding back up, is your engine doing positive or negative work? Positive work. So by the time you reach back to 60 miles an hour, you initially had some amount of kinetic energy, and by the time you get back up to 60 miles an hour, you have the same kinetic energy at the end. And so there is no change of kinetic energy, so the net work would be equal to 0. Okay. Here's the thing. Work is a process. It's not an instantaneous, like when we did the free body diagram, it was a snapshot in time, like poof, what forces are acting on it. Boom, you got an acceleration. Okay. Work is a process. So during this first part, you had negative work. If we stopped the experiment right there, you'd say, oh yeah, there's definitely some network going as negative. But if you looked at just the second part, the speeding up part, you'd be like, oh, look, it's positive work. But if we started the process and stopped the process right when you started at 60 miles an hour and ended at 60 miles an hour, the net process for the whole process would be 0 work done. Okay. The thing I want you to digest is the fact that work is a process. It's not just a snapshot. It's not just a moment, an instant. It's over forces acting over a distance. You okay with that? So you have to define, it's really important to define, hey, what's my initial point? What's my final point? Work is done in that process, in that interim, from that point to that point. Good with that? Okay. And we'll call that good.